Now that we have described how nature evolved, it's time to look at the other important actor in the story, the population and its dynamics. So the net population change is, of course, the births minus the deaths at every moment. So let's assume that we have an exogenous mortality rate of islanders, which is simply D. And intuitively, if there is more food, then population should go up because there should be more offsprings that survive. So assume that the fertility rate increases with the harvest per person. So rewrite it B plus phi that multiplies H at moment T divided by L at moment T. So harvest divided by laborers or population because everybody works. Here B and phi are exogenous constants. So why, you might ask, why are harvests per person? Well, imagine that you have, say, 100 farmers and they have their children. So how many of children will survive per farmer? Well, it depends on how much food each farmer is able to save for each children. So that's why we care about food per farmer. One important assumption that B minus D is smaller than 0. Why do we do that? I let you think for a while about it. Well, if you look at the birth rate, that's the birth rate. The birth rate we get if we have no harvest is simply B. And what we want is, of course, that if we have no harvest, then islanders should starve and the net growth rate of the population should be negative. Otherwise, it would mean that whatever happens for their stock of food, then the population will just grow to infinity, which doesn't make a lot of sense. So then we have the two ingredients, the births and the deaths, and we can now describe the law of motion of population, which is simply, so L dot T, the derivative of L with respect to time, which is going to be B plus phi, which multiplies HT divided by LT. So this is birth rates, minus D, the death rate. And since we want the increase in the level of L, then we multiply by LT. So that's the net rate of change multiplied by LT gives you the net change in L. Of course, now we can substitute the harvesting equation HT equals to alpha beta ST LT. And what we notice is that we can actually cancel LT at the numerator and the denominator. Why is that? Well, it's because the more farmers, then the more harvests, because each farmer can harvest more. But also, the more farmers we have, the more need for food we have if we want the net population to grow. So the two cancel out, and we can get this much simpler expression for L dot T, which will simply be, in the end, equal to LT, which multiplies B minus D, plus phi alpha beta ST. This is the second equation in the system. In the Lotka-Volterra model, this describes, of course, the predator dynamics. How does the abundance of prey affect predators? Well, of course, it affects them positively. That's why we have a plus sign in front of phi alpha beta ST. Here, the higher the stock of food, then the more harvest we have, and the more population can grow over time. Next thing we have to do is, as before, describe how the steady state of the island population will look like. The steady state of the population stock is found in the same way as the steady state for the resource stock. Here I have reproduced the population dynamic. L dot t equals to L of t, which multiplies b minus d plus phi alpha beta st. And so what we want again is the steady state, which means that L dot star, so the growth of the population at steady state is equal to 0. And we again have a function of two state variables, L and S. So of course, both of them need to be at the steady state too. So we replace LT and ST by L star and S star. How many steady state does that give us? Well, it's how many families of steady state I could say. It's let's say we have two. The first one we will call the desert island, and it is simply when actually L star equals to 0. So it means that whatever is inside the parentheses doesn't matter as long as we have nobody on the island. Then if nobody is on the island, the population cannot grow. So it means that S star, the stock of resource, can be any value. It can be 0 or it can be K. It doesn't matter. No people, no population growth. We will call the second possibility again the sustained island, but of course don't confuse it with the other sustained island for the nature. Here it's a sustained island for a sustained population on the island. So when the growth of population is 0, but the population is actually positive. So this means, of course, when inside the parenthesis is 0, which is when b minus d plus phi alpha beta S star equals 0. Note that in that case, L star can have any value. So it means that essentially the growth of the population just depends on S star and doesn't depend on how many people are on the island. If you look at the equation, you can see thus that it is independent of L star. It means that if we have a large enough stock of food, then population grows. And if the stock of food is too low, then the population shrinks, no matter what the actual number of people is on the island. So this means that essentially we have a critical value of S star, which is just a constant that's independent of population. And we can easily compute what it is. So we get that S star equals to D minus B divided by phi alpha beta. And of course, what we can actually do is note that we will never get a star higher than K, because it's never the case that nature can have more resource than K. So let's write that it is smaller or equal to K. All right, so now we have this relation for the steady state of population. And the next step is to again create this phase diagram for the dynamic of L. We reproduce our phase diagram now to show the dynamics of the population. So I have reproduced here in the equation L dot of t equals to L of t, which multiplies b minus d plus phi alpha beta S of t. So again, just to remember, L dot of t is the time derivative of t. And what we are looking for here is to describe how this will change. So how essentially L will evolve over time, given the value of S and the value of L at any moment. And the first thing we want to do, of course, is to start with steady states. They are the easiest to describe. So I've done that here for the more interesting case where L is positive, but here inside the parentheses, this is 0. So this, we found that it gave us as value for steady state S star, which is equal to b minus d over phi alpha beta. And we found that this essentially is independent of the value of LT. So if I want to show on the graph where this line lies. So just think for a moment what this will look like. Well, it should be just a horizontal line, since this is S star equals to a constant. These are all parameters of the model. So we can just show that it should look like this. So these are all combination of values combination of values, because it doesn't matter what L has as value, for which L doesn't change. So that's funny, but really it shows that in that case, the value of L is unimportant. What matters is the value of S, as long as S has this value, B minus D divided by phi alpha beta, then S doesn't change. Then, L doesn't change. So that's obviously the first case. Now we had a second case where actually it's quite easy. L star equals L dot equals 0 when what? When L equals 0, because we know that in that case, if we don't have any islanders, then the population of islanders cannot change, it doesn't increase. So just think again for yourself what this should look like on this graph there. Well, if what we need is L equals to 0, well, L equals to 0 lies just here. So let's show it like this. So this is simply L star equals to 0. Now, can this have any value? Well, no, we had just said that we're going to restrict our set of values for S to 0 and as at most the carrying capacity of the ecosystem. So okay. So this is the whole description of all the possible values of L and S, such that L dot or dl dt is 0, so the population doesn't change. So again, now don't confuse this with the stock of nature. Here we are just looking at the stock of population. Last thing you have to do is to ask ourselves what happens when we are not at the steady state. So to do that, we do as we did for the evolution of the stock of resources. So we can start with any value at steady state. So imagine here. So if this is a steady state, I know that I have a positive value for L. So it means that it cannot be a steady state because L is 0. So it has to be a steady state because B minus D plus phi alpha beta S T is 0. So basically S T has to be equal to S star. And then I ask myself, so for instance, what happens if S goes up? So just think about it. Well, if S goes up, I just have to look at what happens to my equation. S goes up, I have a plus in front, so plus phi alpha beta S of t. So it means that if L dot was 0, now L dot becomes positive. What does that mean? Well, it means that now the stock of population is starting to increase. So we can just write it this way. And think for a second what this means economically. Well, it means that the island was just at equilibrium, in the sense that people were harvesting just enough to sustain the level of population that they had. And then I give them some few extra resources. So what do? Well, they can sustain a larger number of children, and the population can start to increase. And notice that it's going to increase and increase and increase forever, as long as the stock of resources stays above d minus b divided by phi alpha beta. Now, last chance if you didn't get the answer right. So let's do the opposite. Let's start at steady state here again and ask what happens if I decrease S, I hope you have a good idea. So if I decrease S, then the harvest, which is alpha beta S times L, is going to go down because I have fewer resources to harvest. So it means that people can sustain a smaller population or smaller number of children, and the death rate is higher than the birth rate, and L dot is going to be negative, so L is going to go down. How long is that going to go down? Are we going to go to 0? So that's an interesting question. So can here the population go to infinity in a positive fashion, and here go to 0? Well, not, because we have found already that actually the stock of resources S is not fixed. When L changes, then that changes how many farmers are in the island to exploit the stock of resources. So in the end, you cannot, for instance, go for forever to the right, because at some point, if you increase the population too much, then that's people that start to harvest all the food, and then probably that S is going to go down. Same here, if you have fewer people, then you have lower stress on the resource stock, and probably S is going to increase. So we don't see it here, but you might guess that the next step is probably going to be to combine both dynamics into just one global phase diagram for both dynamics to show everything that's happening on Easter Island.